This is the first PowerPoint for Chapter 7, and it's just going to focus on light. I'm going to have to give those sounds going off here. All right, first thing I want to take a look at is we have a rainbow. A rainbow is something that's fascinated people forever. And we know that visible light, when it hits droplets of rain, the light can be scattered into the various types of light that make it up. And we see our pattern here, and the pattern never changes. We have, red and orange and yellow and green and blue and violet. We get that same pattern all the time. Now, early experimenters back in the 1850s, they actually come up with a little device called a spectroscope, which is able to do the same thing as the water droplets do in the air. Here, this spectroscope has a prism, a glass prism that's triangular in shape. And you can see the experimenter here looking through the prism. Over here we have a candle, a lit candle, and what he's actually doing is viewing the flame of the candle after it passes through this glass prism. Now when we take a look at the candle flame, all we see is yellow. Black may be at the bottom, but it's just a yellow color. But if you were to view that through a spectroscope, you would see that that yellow color is made up of other colors. So the glass prism is able to separate that one color into all the various colors that make it up. Now people didn't know why this was so, didn't know why they didn't see those other colors. And what they also didn't know is why when they energized other materials, they got a different set of colors. So let's take a look at light in general now. Although this is where chemistry and physics kind of overlap each other, I'm just going to focus on what we have to know. So light is electromagnetic radiation. That means it has the properties of electricity and magnetism. And light consists of particles called photons. Now these photons are technically massless packets of energy, and they travel in a wave motion. So light has some of the properties similar to sound. Now sound also is a disturbance in the medium that travels in a wave motion. So they both travel in the same way. It's just that sound is not made up of particles. It's just a disturbance in the medium. We're going to check out three properties: the wavelength, frequency, and energy of light. Now here's the definition for wavelength. Wavelength is the distance between identical points on successive waves. Now this is the Greek letter that's used to represent wavelength, and it's called lambda. Frequency is represented by the Greek letter nu, looks like a little V here, and it's the number of waves that pass a particular point every second. The unit for frequency is called a hertz, and a hertz is equal to one cycle or one wave per second. Now you might wonder, what about the unit for wavelength? Well, since it's a distance unit, we can use any distance unit that we had previously. We're going to see two of them. We're going to see meters and we're going to see nanometers. Now here's the comparison of red light versus blue light. Now if we take a look at this here, we have red light and blue light, and these circles represent the photons of the light. You notice that the photons of red light are smaller than the photons of blue light, and this is supposed to indicate that the photons of blue light have more energy to them. Now you want to notice that the number of waves of red light is smaller than the number of waves of blue light. So blue light has more waves here. And so blue light has a shorter distance between the waves, so it's a shorter wavelength than the red light. And the frequency of the red light is lower because the frequency is the number of waves. So we could actually count these waves and say there's 1, 2, 3, 4. This could be 5 waves per second, whereas for the blue light we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 waves per second. So you notice that the frequency of the blue light is double the frequency of the red light. And we could actually indicate that maybe the energy of the blue light is twice that of the red light. So the longer the wavelength, the lower the frequency and the lower the energy of the light. And then for higher frequency, we have a shorter wavelength and also a higher energy. So these properties kind of go hand in hand. Now here's a chart right from your book. If we check this one out, this is a nice one because it gives you many different types of energy that you might be familiar with. Now let's take a close look at it. So we have gamma rays, X-rays, and ultraviolet light. These are all very highly energetic light The light here is strong enough to knock electrons right out of atoms and to cause chemical reactions to occur. Now, we're all familiar with ultraviolet light in the summertime causing sunburns, and so that tells you that it's pretty strong light. We don't think of X-rays being that strong because we don't see the X-ray, we don't feel it when it hits us. But you notice if you ever had an X-ray, the technician always leaves the room, so there must be something going on there. As we continue to the right now, we have the small part of the light that we can actually see. This is the visible light. We can see the pattern. We saw that before with the rainbow. So purple light has the smallest wavelength, and here it's measured in nanometers, and red light has the longest wavelength. So you see these colors are really a band of wavelengths. It is not a particular number for it. So this is just what we can see. Now, to the right of the visible spectrum is energy that we can't see. This energy is not strong enough to cause chemical reactions to occur, but it can increase the speed of molecules, and thus it can make them move faster or slower. So infrared light we see is really heat. If we could see heat, it would look red. It's just below the spectrum that we can actually see. And then as we go, as the wavelength gets longer, we get into microwaves. Remember, you probably have a microwave oven at home. You don't think about radar too much, but radar is in the same band. It's all in here. And you notice here, microwaves, we have cell phones. Now, if you notice this picture, it looks like an old phone, and it is. But even the cell phones we use today, they communicate by using microwaves. And as we continue to the right, the wavelengths get longer and longer, the energy becomes less. Now we're into TV and finally radio. So you notice that FM radio has a shorter wavelength than does AM radio. And if we look up here at the numbers, let's say we start at the wavelength. In nanometers, this is extremely small. That would be 1,000th of a nanometer. And remember that a nanometer is a billionth of a meter. So that's really tiny. So as we go to the right, the number of nanometers is increasing. So visible light is less than 1,000 nanometers. And we can see that down below. And then it jumps quite a bit. So we go from 1,000 nanometers up to right here at 10 to the 9th. This would be 1 billion nanometers, which is equal to 1 meter. So once you're up at this end here, we're going to be measuring the wavelength not in nanometers anymore, but in meters. And if you notice the frequency, look at the power of 10. It's getting smaller all the time. The one thing you might want to notice is if you multiply these two together, you wind up adding the powers. And notice that we keep getting the same number all the time. This would be 10 to the 1st. So what do we get when we multiply these guys together? We see 10 to the 17th. So there is a simple mathematical relationship between the wavelength and the frequency. Now, if we take a look at some light, this is purple light that's being produced by heating hydrogen gas. So we have actually, I shouldn't say heating. We have hydrogen gas in this tube, and we're using electricity to cause a light to be produced. So if you could see this, you would see the light is purple color. And if you had that light go through a small hole, if we use my arrow again, a tiny hole, looks pretty big here, but coming out, then it would come out as a beam. And once it hits that glass prism, you'd see that the light would be scattered into these 4 lines. This is called a line spectrum. So hydrogen always produces that same line spectrum. And this technically is the fingerprint for hydrogen. There's no other gas that produces that. Now we could write it this way. We can see actually we could identify the particular wavelengths. So this is unique for hydrogen. And actually, as it turns out, a line spectrum, and notice it says emission, meaning energy is being produced. A line spectrum is unique for all compounds and all elements. So it's a way to identify compounds and mixtures or elements and mixtures simply by energizing them. And when you do that, you wouldn't be destroying anything. You wouldn't be causing chemical reactions to occur. So it can be a non-destructive test. Now, let's check out all the different emission spectra that we would get from a whole bunch of different elements. So you notice here, lithium, you see a few colored lines. It might be kind of hard to see these two. Look at the 2 bright lines here for sodium. If you ever heated water on a stove, a gas stove, when the water boils over and hits the flame, you see the blue flame turn yellow or a bright orange. And that's really because of the sodium that's in the water. Now, besides sodium, there are other minerals in the water, and they also would turn color. So you see suddenly the flame changes color, and that's due to these metal ions in the water being energized. Now we wouldn't see any of these colors ourselves. Look at all the different lines for barium. So what would happen if you had a mixture of these elements? Then you get a mixture of lines. Right, now we're going to take a look at the math involved with light. So we start off with a simple equation. The speed of light is equal to the wavelength times the frequency. And these are the symbols that we're going to be using. A small c will represent the speed of light. These are the Greek letters that represent wavelength and frequency. If you recall from earlier, this is lambda and this is nu. Now I found for many people, it's easy just to replace these two with W and F so we know exactly what we're talking about. So this is wavelength and frequency. So we're going to be using that equation in a couple of problems. Now we want to remember a couple of values for the speed of light. So sometimes we want to use this one. This is in meters per second, 3 times 10 to the 8th. When we talk about visible light, we're going to be talking about measuring it in nanometers per second. So this is just another form of the speed of light. Notice it's 10 to the 17th. Now in this country, we also talk about the speed of light in miles per second. I remember as a youngster having to memorize that number. We never did anything with it mathematically, but I think it was just to see how fast it is. All right, so let's take a look at a problem that you might see similar to the homework assignments. So you're asked to find the frequency of green light that has a wavelength of 500 nanometers. You can see the 500 up here. So we'd start off with writing our equation. C equals wavelength times the frequency. And since we're looking for frequency, we want to solve the equation for frequency. So I divide both sides by wavelength, and the wavelength would cancel out. And so then I wind up with the speed of light divided by the wavelength equals the frequency. Now because I was given a wavelength in nanometers, I want to use the speed of light that has nanometers in it. So in my solution, I take my speed of light, 3 times 10 to the 17th nanometers per second, and now I'm dividing it by 500 nanometers. And you see how the nanometers would cancel out. And I'm going to wind up with a unit of 1 over seconds, which I'm going to write as seconds to the negative first. And a seconds to the negative first really is called a hertz. And this looks like an awful lot of them. It is a lot of cycles, but we could talk about light with having an awful lot more than this or a lot less. So this is the first type of problem you're going to see, where you're given either the frequency or the wavelength and you're asked to find the other factor. Here's a similar question that you might see about radio stations. So here we were asked to find the wavelength in meters of the radio station WROR, and this is the numbers for the radio station. And this is a Boston station. Some of you might even listen to it. So first of all, I want to tell you, what does the FM stand for? Well, it means frequency modulation. And as far as the number in front of it, this is actually going to give us the frequency of the light. So for all FM stations, they broadcast in what we call megahertz, or millions of cycles per second. So the frequency for this particular radio wave is 105.7 times 10 to the 6th hertz. So this is what we're going to be using in the problem. So you could do the same thing for any FM radio station. Just take the number of the station and multiply it by 10 to the 6th hertz, and that's its frequency. Now what about AM? Well, AM broadcasts in kilohertz, so instead of 10 to the 6th, it would be 10 to the 3rd. You might see a problem in the textbook that asks you about FM stations. And again, here we have our speed of light. Now you might wonder, why are we going to measure it in meters per second? Well, if you look back at that diagram that we had all the different types of light on it, once you get up into radio stations, you're talking about a pretty good wavelength distance. So we want to use meters per second. So let's set up the problem then. So we're going to take our formula. We have speed of light equals wavelength times the frequency. And this time we're going to solve it for wavelength. So that means we're going to divide it by both sides by the frequency, and then we wind up with C divided by the frequency equals the wavelength. And then we plug in the numbers. Now here's C, and here's the frequency down here. Now the seconds to the negative first would cancel out with the seconds, and then we wind up getting 2.84 meters for an answer. So you see, this is the right unit to have. So 2.84 meters. A meter is a little bit longer than a yard. And this is getting up to about 3 yards, or around 9 feet. So you could do the same for any FM station. Now, if we go back and check out our formulas, this is what we had so far. And now we want to talk about the energy of the light. Well, the energy of a photon can be calculated by taking a value called Planck's constant and multiplying it by the frequency of the light. So this is going to be our formula. E, representing the energy of a photon, is going to equal Planck's constant, which is going to be represented by a small h, times the frequency. So you can say h nu or hf. And this is the value of Planck's constant, 6.63 times 10 to the negative 34th joules times seconds. So that's a constant that makes this equation work. So if you're asked to find the photon energy, you need to have the frequency. So if you start off with the wavelength, then you find the frequency, and then you can use this equation. So if we go back to the problem you had earlier, you were asked to find the frequency of the green light. So let's say now we want to find the energy of that green light. And now we have the frequency from the previous problem. So I'm going to take my formula, E equals HF. I just have to plug in my values. So this is my constant, joules, seconds. This is all part of Planck's constant here. And here is my value from the problem. And when I do this again, seconds will cancel, and I wind up getting a value of 3.80 times 10 to the negative 19th joules. Now a joule is a unit of energy. It's much smaller than a calorie. And so this is a very tiny, if you look at the power of 10, this is a very tiny amount of energy. But we're only talking about one photon. And you would never have just one photon produced by a bunch of atoms. You would have billions and billions and trillions. So it might be interesting to figure out, what is the energy of a mole of these photons? Remember it says mole, and we're counting things. We're going to be using Avogadro's number. So if I just take my answer from above, this is the energy of one photon, and this is Avogadro's number, then you'd have this many photons in a mole of photons. And multiplying them together, you see the photons would cancel, and you wind up getting 2.29 times 10 to the 5th joules. Now we get some appreciable energy. Okay, and that's the end of the show.